Right. Thanks for showing up. I know it's kind of a different talk compared to the others. So, how many of you guys are familiar with TI graphic calculators? Everybody in here? Okay. A lot of people are probably familiar with them from school. They're very expensive, very overpriced devices that schools require you to buy or use for math class. Some people are probably also familiar with the fact that they're programmable, that you can make them do all sorts of things, from helping with math assignments to taking notes for science classes, other classes, and then of course for playing games. Yeah, that's what we really care about. But what people outside the community might not know is that they're good learning tools for getting into programming and reverse engineering. And a big chunk of what the community knows about programming graphic calculators we know because we figured it out ourselves. So we wrote code not knowing what was going to happen. We run tests not knowing if it was going to mess up the hardware, experiment with it, and so on. So that's never more applicable than with trying to break the security that's built into these things. And why we would want to do that, we'll be getting into. So my goal here is to provide a personal and historical overview of what the calculator community is, how it started, the major things that have happened in it, where we're at now, and hopefully where we're going with it. Starts out as kind of like an overview, but it gets really technical really quickly, and I've got a lot to get through. There's a lot of slides here, so I'm try to talk fast. But if you have a question, just let me know. So who am I? I'm just a guy with a lot of calculators, probably too many of them. They're what got me started in the software development industry, and now this is what got me started in the security industry. These are not complete pictures because I do have more than what you see here, but as far as I know, it is the world's largest collection of Texas Instruments graphic calculators and accessories. And by that I mean in terms of variation. There are one or two people that have more of them, just in terms of sheer numbers, but as far as every model, I have at least one of every model that's ever been mass produced. So that's every model from all over the world, every hardware revision, every color variant, except for one, because there's just so many different colors. Every view screen or teacher's edition version, every easy spot yellow school version, and a number of one-of-a-kind, or close to one-of-a-kind, prototypes and engineering samples. So, I grew up with these things. They gave me my career, my life, so I love them, and I want to make sure that that they can do absolutely everything that they're capable of doing, and maybe a little more, and make sure that everybody else can too. Because I'm not the only one. They've actually jump-started a lot of careers and knowledge about low-level engineering, embedded devices, software engineering, and hardware and software. So my hope is that I can share with you a little bit of my journey with these devices, how far they've come, and maybe you'll learn something, or at least be entertained. So what is a graphic calculator? Well, first and foremost, it's a calculator. It's capable of doing everything a scientific calculator can do, but it also has a large screen capable of graphing equations or tracing, so you can trace solutions along the graph or draw on it, whatever you want. It's got a 2.5 millimeter I/O port, or in some cases USB, so that you can share variables and programs between two calculators, or you can connect it to a computer and share them with anybody in the world. They're programmable, which means you can create programs, like I said, to solve math or engineering problems, and you can do that using a basic-like language that TI invented called TI Basic. It does have some very basic commands for programming games, like gathering key press input and drawing on the screen, but it's way too slow to really utilize the hardware to its maximum potential. So for that, we have assembly language, and in one form or another, every model, with the exception of the TI-80, which is being worked on, every model is capable of running arbitrary native code. So some of them have this capability built into them, and then some of them had to be hacked first by the community. So the models that came first were the Zilog models, or Zlog. I'm pretty sure you can pronounce it Zilog, but I've always said Zlog, so I might slip into Zlog without realizing it. But these use the Zilog Z80 processor, which is a very old processor that's used in a number of devices, old devices and new devices, because it's actually pretty nice. It's a very versatile chip. It's 6 megahertz, or on some models it's been sped up to 15 megahertz. It's an 8-bit CPU with 16-bit addressing, which means it can access a maximum of 64 kilobytes of memory at once. And it has an 8-bit I/O port interface, so you can interact with the hardware by outputting or inputting from one of up to 256 logical ports. And they have anywhere from 32 kilobytes of RAM all the way up to 128 kilobytes. And some of them, the most interesting ones, have flash memory, which ranges anywhere from 1 megabyte all the way up to 4 megabytes. Now, the first model capable of running native assembly programs was the TI-85, which is a very old model that you don't see a lot of these days. Rumor has it that TI employees actually had a bet as to whether we'd figure out a way to run native assembly programs. And that turns out that was a safe bet because the community did figure out a way. And it was through something called Z-Shell. Now to explain how Z-Shell works, I have to elaborate on on a particular feature that some of these old models have, and that's to transfer backups via the TI GraphLink I/O cable. That's that little 2.4mm I/O cable. That's what connects them to the computer. And so these backups are actually just dumps of the entire RAM, not just where variables are stored, but the system's RAM as well. And there's also, the calculator's operating system also supports something called custom menu entries. That's what that red arrow is pointing to, the custom button on the keyboard. And so you could add your most commonly used OS commands in here and be able to access them. Just one or two tabs. And interestingly, the way the OS stores things in this menu is by just keeping track of the address of the code that would handle this OS command if you selected it, if you ran it. And it keeps track of this in system RAM, which is included in that computer backup. So what that means is all you have to do is change the address of one of these custom menu entries to point to code that we also embed in that RAM backup, and you got code execution. And that's what Z-Shell is. It's just a small program that lets you run other programs so that you can write you can write programs to store them on the calculator in the form of string variables. Then the TI-82 came along, and it also had to be hacked in order to enable executing native assembly code. Unfortunately, though, it has no custom menu, so another method had to be found. But it does have memory backups, so we start taking a look at other things that are stored in system RAM. Now, the operating system on the calculator is essentially just a series of what are called contexts, which are just kind of like built-in applications. Things like the home screen, the equation editors, the graph screen, things like that. And each context has a table of addresses that point to handlers for different things, like what happens when you press a key. And the key press handler is the most important one. It's called the CX main handler. And whenever you switch to a new context, these handler addresses get stored in system RAM. So our goal is to find a way at runtime to override that CX main handler. And that's done by another piece of functionality that is storing values to variables like real variables, like mathematically real variables, complex variables. Those are stored in RAM as 9 bytes, and then when you copy from one variable to another, those 9 bytes are just copied from the source variable to wherever the data for the second variable is. So if we modify one variable like x with the bytes that we want, if we modify it with the address of code that we embed in that memory backup, and then modify the location of a second real variable like y to point to CX main instead of the actual data for that variable, then we can override CX main by just storing x to y. So it just copies 9 bytes from one place to another. So once you do that, CX main's overridden, and then the next time you press the key, you've got code running. So that gives us a shell with which to run other programs, just like Z-Shell on 85. Then came along the TI-83, except this model actually has a backdoor in it that TI put there, which allows directly running assembly programs that are stored in RAM. And that backdoor is hidden in the send command, which is normally used for transferring variables from one calculator to another using that 2.5mm I/O port. But if you put a 9 right after the command, it won't transfer the variable, it'll instead execute it as though it were native code. So the TI-83 is the first calculator I ever had, so this is right around the time that I got into the community. And then when TI saw that there was a big booming interest in assembly programming through this backdoor, they decided to add really nice assembly support to the TI-86, which is a new and improved TI-85. And that calculator has a brand new command, ASM, which is intended for running assembly programs right from the beginning. So they not only provided some basic documentation for how they use system RAM and how user RAM is laid out, they even included OS hooks so we could integrate with the OS and expand its functionality, which is really cool for its time. It was really ahead of its time. And then came flash technology. So these to me are the most interesting models because they are upgradable in terms of OS upgrades, flash applications, which have tighter OS integration, and they're stored in flash instead of RAM, USB ports, and security implementations to protect some of that functionality. And whenever something's designed to keep you from doing it, you need to get into it. So, just to note, in Europe, they make these model numbers really confusing. It makes it really difficult to collect them. So, first they made the TI-83, then they made the TI-83 Plus, And then they made the T84 Plus. So there was never actually a plain old T84. They just went straight to the Plus. So that would lead you to believe that because it doesn't have plus in the name, it might not have flash memory, but actually just doesn't even exist. And then they made a model called the T84 Pocket.fr, which is just a physically smaller T84 Plus. So it is a plus, but they didn't put plus in the name. But it's otherwise identical in every way. And then they made a T84 Plus Pocket SE, which is just a physically smaller T84 Plus Silver Edition, except they did put plus in the name, so it's just a mess. And then there were all sorts of duplicates of the exact same calculator, so they just slapped a different name on it. So like the T82 Stats and T82 Stats.fr, FR means French, by the way, they're really just T83s. Then you have the T83 Plus.fr, which actually could be referring to two different calculators. They use the exact same name for two different calculators. One is just the T82 Plus, and then the other is the T84 Plus Silver Edition. Then there's the T82 Plus, which is just an 83 Plus, the exact same thing, they just put 2 on instead of 3. And then the T83 Premium CE, which is exactly the same as the T84 Plus CE. And then they made the T84 Plus T stands for test, but that's actually just the T84 Plus Silver Edition, so it's insane. And they're still releasing models, they just released 2 more. So while the Z80 models are by far my favorite and where I'm the most knowledgeable, there are of course others, such as the Motorola 68K models. These started with the TI-92, which came out around the same time as the TI-85, and it has a QWERTY keyboard, which is cool, but unfortunately that gets it banned on most standardized tests because it's technically considered a computer if it has a keyboard like that. One thing that's unique about this model is that it actually has an expansion port on the back of it, which would let you add features or even turn it into an entirely different model. So these models are really rare. There's the TI-92 module, TI-92-2 module, then there's the TI-92E module, E for Europe, and that just adds more RAM and language options to it. And then there's the TI-92 Plus module, which is by far the most interesting one. It's equally as rare, though, and it turns the TI-92 into a TI-92 Plus, which gives it flash memory and upgradability. And that model is basically the same as the TI-89, which is that black one at the left, except the TI-89 doesn't have a QWERTY keyboard. And then the TI-9 Titanium next to it in gray, which has some minor hardware changes, and it adds a USB port to it, which turns out to be really useful. Then there's the TI Inspire models, which are ARM-based. I really hate these calculators because they're really big and bulky, and they're not really useful. They're more educational tools, they're not really practical devices, but they do have swappable keyboards, and probably the most significant one is the T84 Plus keypad. That's the most significant keypad, which if you snap that into it, causes it to emulate a T84 Plus, which makes it kind of sort of useful again. And then there are versions that don't have a CAS, and then versions that do. CAS means Computer Algebra System, so that's helps with higher math. And then they have the TI Inspire CX models, again both a CAS and a non-CAS version. Those have color LCDs, and they're redesigned to be a little bit sleeker, but they still kind of suck. So. Another big reason I hate these is that they're completely 100% locked down, unlike all the others, completely 100% locked down. No way to execute native code at all, unless you jailbreak it, for lack of a better term. There's something called Endless. It's kind of like Z Shell that lets you, it re-enables unsigned code execution on it. For some reason, TI fights this really hard. They try to fix vulnerabilities that it uses as soon as they can, way more than the other models, which is unfortunate. But why they would focus on the worst ones, I don't know. But and then finally, we have the EZ80 models. These are the newest models that have color LCDs. If you go to Walmart, this is what you see. Unlike the Z80 models, these have what's called an EZ80, E for enhanced, I guess, nobody really knows. This CPU supports 24-bit addressing, and it has backward compatibility with Z80 code, which they don't use, but it was designed for that. The ASIC and the hardware interface that's inside of the calculator is completely new. It's totally redesigned with security in mind. So unlike the Z80 models, which have like a paging or bank switching system, the EZ80 models have a flat memory model, which will be interesting. They had to change the security based on that, but they should have anyway. The T83 Premium CE, hardware-wise, is identical to this model, but it has a different OS on it, which includes an exact math engine, and that's only sold in Europe. So one thing TI really wants to prevent is being able to run that nicer OS on the US T84 Plus CE, but they're not going to succeed in that. And then there's the T84 Plus CE-T, T for test, which is the European version of T84 Plus CE. It's actually got a testing LED on it that blinks during a test, so you know that it's in like a special testing mode where you can't access documents or notes or anything, so you can't cheat. So a teacher can look at your desk, and if it's blinking, they know you're not cheating. But it can be gotten around. So, having said all that, there are some really cool things you can do with these that have absolutely nothing to do with calculators, nothing to do with math or school, or even games. Since some of these models have what are called on-the-go USB ports, it's possible to connect any number of USB peripherals to it. So instead of plugging in the computer, you can also plug other devices into it. So anything from Bluetooth or Wi-Fi adapters, so the calculators can communicate wirelessly with each other, to serial adapters, to keyboards and mice, even USB flash drives, hard drives, floppy drives. All of that actually exists, except for the Wi-Fi one, because no one wants to write that. That's a lot of work. But the others do exist. And they have these calculators have a very unique on-the-go USB controller, and one that's really flexible and allows you to do things that you really should not be able to do, real abuses of the USB protocol. And the best example of that would be the PlayStation 3 jailbreak, which, does anybody remember when the PS3 was jailbroken? Yeah, okay. So that happened shortly after other OS was taken away. Long story short, there was a USB-based exploit that required connecting a Teensy or similar device like that to your PS3 to enable unsigned code execution. But when it came out, of course, Teensies all over the world sold out and were back ordered. Nobody could get them, so they needed some other way to trigger the exploit. So I looked into how it worked and realized that it's basically simulating a USB hub, and it's virtually attaching and detaching devices in a very particular order to trigger a memory corruption exploit. And the way that it does that is the USB peripheral, like the Teensy, has to be able to pretend to be other USB devices temporarily by changing its own address in software, so that it can pretend to be these virtual devices that it claims are being attached and detached. And that is something that the calculators are able to do. So I implemented it, and like 2 days after that came out, people were able to jailbreak the PS3 using one of these calculators. And then, of course, you can also simulate other USB devices as well, such as USB keyboards, mice, even the Skylanders portal, the Disney Infinity portal. I've even booted a calculator or a computer off these calculators by having pretend to be a USB flash drive with a bootable image on it. And then, of course, you can use it for other things too. So, why have security in calculators? Well, when flash memory first came into the calculator world, TI actually sold flash applications for $7 and $15 a piece in their online store. And these would range anywhere from pocket organizer applications to spreadsheet applications to periodic table applications to everything to enhancing the built-in math capabilities. They even released games. And they would provide an SDK for free so that you could make your own, but then they would charge $99 for the right to release 3 applications in their online store, or for free. So they charge $99 for you so you could make 3 free applications. And naturally, they wouldn't want these applications to be pirated, so they had to restrict how and where these applications would get installed. And then, of course, they also want to prevent cheating in the classroom. So you can't have students accessing notes or that they typed in or programs that would solve their problems for them during tests. So they had to. They wanted the calculators to have, like I mentioned before, have some kind of restricted mode for the duration of that test, so that they can't look at notes or view programs that they wrote or just type notes into it. And then they wanted to prevent tampering of the operating system, so where we could, because if we could modify the operating system, then we could just easily patch out these security mechanisms. In fact, I'm convinced we could actually make a better OS than them in terms of math capability and performance if they would let us do it. So we're going to have to figure out a way to get it on there. So it's not really that TI wants to enforce all these protections. It really amounts to pressure from educators and schools, teachers, types of people like that. So they're forced to create anti-cheating applications like something called Test Guard, which you can connect to another calculator and remotely delete or disable programs and applications. And they have something called Press to Test, which is a feature in the OS where you can hold down a key combination and it puts it in that restricted mode. And you can't get out of it until you transfer another variable to it. So if you're in the classroom, they could just come by and press those keys, and then you can't run games, you can't do anything until you get back home and connect it to your computer. Which that doesn't keep anybody else from doing the same thing. So if somebody really hates you, they can just walk up to your calculator, press those keys, and now you're locked out. So I really don't like that feature, which is one of the reasons I got rid of it. And then there's the user community. That's another key player in this that wants to be able to maintain control over this really overpriced hardware that we're maybe forced to buy, and want to do cool things with it. So there's countless numbers of things we can make them do, which not only help the calculator community, but help with other things like the gaming console community. So now that we know a little bit about who those, who the two key players are, we'll start getting into the technical parts of how these work and how the security is implemented in them, and how we can, have, and will continue to defeat. So at a hardware level, the Z80 models really gets us to three things. You have the ASIC, which is, and then the flash chip, and then all the other hardware that the ASIC interacts with, such as the LCD display, the USB ports, the I/O ports, the keyboard, and all that. Now, this is not 100% accurate because the hardware has changed over the decades. For example, the RAM wasn't always internal to the ASIC, and neither the ASIC, by the way, is the chip. All this stuff is built into that singular chip. So the RAM wasn't always in there, and neither was the CPU. But this is the most common configuration that you come across. So as I mentioned, the Z80 is a 6 megahertz CPU, 16-bit addressing, can only access 64 kilobytes of memory at a time. So since the OS is much larger than that, they have to utilize something called bank switching, which is where that 64 kilobytes is split up logically into 4 16 kilobyte pages or banks. And each of those banks can hold any 16 kilobyte region of memory that you want. So if what you want to access is currently swapped into one of those 4 banks, you just reconfigure that bank so that it points to the 16 kilobytes that you want, and then you access it by accessing the memory address for that bank. As far as accessing the hardware, the Z80 has 8-bit I/O addressing, so there's a maximum of 256 I/O ports that it can talk to. And the purpose of each I/O port is different for each model, but the flash models all follow the same basic pattern, which is everything from port 0 all the way up to port AF. They do everything from ASIC configuration, LCD access, keyboard input, USB control, everything. So there are a few rules about how the bank switching works in the 83 Plus and 84 Plus series. Like I said, it's split up into 4 banks, 16 kilobytes each, starting at address 0, 4000, 8000, and C000. The first bank, except for some weirdness during the cold boot, it always has ROM page 0, which is the start of the OS. And then the second bank is constantly being used to swap in different chunks of the OS, which is way bigger than 64 kilobytes. I'm constantly swapping in what it needs when it needs it. And then the third and the fourth banks typically have RAM pages swapped in, meaning there's usually 32 kilobytes of RAM accessible to the OS at any given time. Some of that is user RAM, and some of that is the hardware stack. And then the rest is system RAM that the OS can use internally. And as you can see, the last 3 banks all have I/O ports that control, hopefully you can see that. The last 3 banks all have I/O ports that control what page is swapped in. So if you want to swap ROM page 1 into the second bank, you just write a 1 to I/O port 6. That's the second box there. Or if you want to swap RAM page 81 into the third bank, you write 81 to I/O port 7, which is the third bank there. So now the most important I/O port in the entire ASIC is port 14, which controls flash unlocking and relocking. So whenever the flash chip is locked, which is almost always the case, write and erase commands to the flash chip are ignored. So essentially you can't modify flash until you unlock it, and the only code that can unlock it is the flash, so it can only modify itself. So it also controls whether certain I/O port values can be modified. So if a port is like that, we call that a privileged I/O port because flash has got to be unlocked before you can write to it. So it doesn't always deal with flash, that's just what it's come to be known by. And the way it works is very simple. You just write a 1 to unlock it or a 0 to lock it back. What's not simple, though, is that you can only write to that port in certain circumstances. There's a special sequence of Z80 instructions, which are those 5 there. There's a certain sequence of instructions that, like IM1, interrupt mode 1, and DI, disable interrupts, that has to be run in order for writes to that port to stick. And those instructions explicitly prevent interrupts from running and interfering with this process, so you can't steal control while this is happening. The privileged page ranges are mentioned there, but as you can see, the only pages that are allowed to modify flash, are the flash, which is the OS and the boot pages. So you can't modify the OS unless you are the OS or the boot code. So that leaves us out of luck, or so it would seem.
Question.
Yes.
The special sequence is just required to make it work, or is enforced to prevent?
It's required. It's required to make it work. If you don't have knob IM1 DI, if you just simply put 1 in A and then write output A to port 14, nothing happens. It gets ignored. So writes to that port are ignored unless that it's preceded by those instructions.
So there's some hardware that's looking at what instructions are going on.
Exactly. Yeah, there's hardware that actually looks to make sure those instructions are fetched from a privileged page. Otherwise, the write's not going to stick. Which I'll get into in a second. So to give an example of how TI uses this protection, there's logic behind receiving. Well, here's the logic for receiving and installing an OS upgrade. So in a loop, the boot code will one, receive a chunk of the OS data and where it should be written to on the flash chip. And two, unlock flash using that privilege sequence, and then writing a 1 to port 14. And then it checks for a whole bunch of tricks that we might use to steal control away while it's unlocked. And then 3, it writes the OS data to the specified area of the flash chip. And then finally 4, it relocks flashback using the same privilege sequence as before, writing a 0 to lock it back. So anytime the OS does something involving modifying flash, it will unlock it, perform some simple operations as quickly as it can, and then relock the flashback to try to minimize any type of exploit. So as I mentioned, it checks for trickery. Specifically, it checks, one, it checks to make sure that the SP, the stack pointer, lies between C00 and FFF8, so that's the last bank. And it does this to make sure SP is pointed somewhere in that last bank, somewhere in RAM, so that when it returns back to the caller, it gets what it assumes would be a valid return address from the stack. So you want to make sure you can't mess with that. 2, it checks to make sure port 6 contains a privileged flash page, because that's where any flash unlocking code would be running from. 3, it checks port 7 to make sure it contains RAM page 1, which is where system RAM is and what the OS would consider the normal operating scenario. And then 4, it complements the bytes at 8000 and C000, which confirms that the 3rd and 4th banks contain writable RAM pages, and all of those straight second byte decimals. So in addition to this, there is hardware checks, which we'll get into. So why would TI care if we point SP, or the stack pointer, to an area of flash? Well, let's try it and play it out. For starters, modifying flash is complicated. It's not as simple as loading a register value to a memory address. It requires a sequence of memory mapped commands like get chip ID, erase sector, program byte, things like that. So if we point SP to a location that's definitely in ROM, such as 1000, which is in the first bank, it's deep in ROM page 0, the first bank, and then we jump into some code that unlocks flash and calls some sort of subroutine, something interesting will happen. The call instruction is going to attempt to write the return address to the location pointed to by SP. But because SP is pointing to ROM, like in this screenshot, there's a bunch of 80 bytes, those writes are going to be ignored because it's not following that sequence of instructions, the flash chip instructions that need to happen. So when that subroutine finally encounters a return instruction, it will do what the return instruction always does. It reads the first 2 bytes pointed to by SP, which is 80 and 80, and it'll jump there. So that means it's going to jump to address 8080. Not at all what the code intended to do, but because we messed with SP, it's exactly what happens. So this would be a really cool way to steal control away from the OS and the boot code, but they did think of that. That was the point of that check. So what do we try next? Well, this is where the hardware is interesting. We learned through experimentation that the privilege sequence of instructions only needs to be read from the privileged page. It doesn't necessarily have to be executed from that page. So that requires thinking about what actually happens on the data bus when instructions are actually being executed by the processor. So when it goes to execute the RLC, which is rotate left with carry instructions, the first yellow one, it first has to read the bytes or the opcodes that make up that instruction. That's how it decodes that it is RLC. And because it uses index register IX, that's a 4-byte instruction in Z80, so it reads DDCV0000 from that privileged page. And then it has to actually execute that instruction. And to do that, it has to read the 3rd byte at IX at offset 0. That's the ED byte from the privileged page. So there's an awful lot that goes on just in that one instruction. Then it goes to execute the load HL into D instruction. That's the second yellow instruction, which means it has to read that opcode. So that's 56 from the privileged page. And then it actually executes it, which means it has to read the F3 byte from the privileged page. So the Z80 equivalent of all those instructions, all those bytes, is nop nop IM1DI, which is the unlock sequence. So if you proceed the output to port 14 with all that, and you set up some memory, you set up IX and IL, set up some memory correctly so that those bytes will be fetched, then it'll work. And the big advantage here is that none of those instructions actually disable interrupts. They don't set interrupt mode 1, which means that after it runs, we could steal control away from that code, or allow other things to run. You could have interrupts run while you're doing some privileged instruction. So all we have to do is find the instructions in yellow on a privileged page somewhere. Unfortunately, though, they're not anywhere on there. And so as awesome as this is, we can't use it. But it's useful if we make our own OS, because now we can unlock flash and write to it without having to disable interrupts. That's something TI can't do. Since we don't care about the security, we can. So, well, then comes along the TI-3 Plus Silver Edition, which is an enhanced version of the TI-3 Plus. It has 128 kilobytes of RAM instead of just 32 kilobytes. It's got a flash chip twice as large, and its CPU is capable of switching between 6 megahertz and 15 megahertz, so it can actually run faster at certain times. Its ASIC got a few upgrades as well, namely I/O port 5. That's a new I/O port. And this I/O port actually allows controlling the RAM page that's swapped into the last bank, that fourth box, something that you couldn't do on the original 83 Plus. The thing is, though, TI didn't actually update their flash unlock trickery checks to validate that the value of port 5 makes sense. So this can be used to our advantage. So the OS always expects RAM page 1 to be in the third bank, and it always expects RAM page 0 to be in the fourth bank. But what happens if we swap the RAM page into the last two banks? So both of them have the same RAM page in it. Well, now things are all kinds of screwed up. Even though SP, the stack pointer, which has to point in the last bank, even though it's pointing there, the stack is not there anymore. So now we have the same page swapped into two banks at the same time. So if I were to write a value to the first byte of the third bank, the first red box, I would actually be able to read that same byte from the first byte of the fourth bank, the second red box. So that's definitely very interesting. So what we need to do is we need to find a section of the OS or the boot code that unlocks flash, writes a value into the third bank, which is where system RAM is, and then attempts to relock flash back. And as luck would have it, there is a very convenient block of code that does that. There is a particular bit, and in fact an entire byte, of the certificate region of flash that holds whether the OS is valid or not. If it's valid, as it usually is because you're running code on it, the value will be 0. So what we can do is jump directly into the boot code at the point that it unlocks flash just before it reads this byte from the certificate. It will read it and it will store it to an area of system RAM called OP1, which is in the third bank, and it's at address 8478. So since we've just used I/O port 5 to swap RAM page 1 into both of the last two banks, writing a 0 to 8478 will also write a 0 to C478, which is exactly 16 kilobytes ahead in the fourth bank. So if we can craft things just right, we can set the stack pointer, SP, so that by the time it gets to that write, to 8478, SP will be pointing to C478, so it'll corrupt itself. So when it performs that write, it'll corrupt the return address that SP is pointing to. So if the return address used to be 46E1, writing that 0 will change it to 00E1. So as soon as the code hits the return instruction, it's not going to return to the boot code. It's going to return to 00E1 instead, which is deep in the OS interrupt in ROM page 0. And we can use an OS cursor hook at that point to steal control away from it, clean up the stack, restore the value of port 5 back to what it originally was, and we still have flash unlocked. So ready for us to use. So that's great, but this port 5 trickery only works on the 83 Plus Silver Edition and up, not the original. Because the original 83 Plus has no port 5, so we'd be out of luck there. And even worse, we had to use an OS hook to steal control back. We had to hard code the value of SP based on the call stack for that particular OS version, and we had to hard code a return address that starts with 0, all of which could change from OS version to OS version, or boot code version to boot code version. So what would be really nice is if we had something that worked on every model, every OS version, every boot code version, every hardware revision. To do that, well, you're going to have to tack functionality that not only exists on all models, but isn't likely or even able to be changed easily. One such feature is the OS's ability to receive flash applications from a connected computer or another calculator. Since flash applications are fixed multiples of 16 kilobytes in size, even the smallest flash application can't fit in RAM all at once. So that means the OS has to, in a loop, receive a chunk of flash data, unlock flash, write that to an arbitrary location of flash, arbitrary is important, and then relock flash back over and over again until all the application is received and written to flash. Now that functionality has existed in every OS version for every model since the beginning, and they can't take it out. So if it's possible, that would be the perfect thing to attack. Before jumping into the OS code that unlocks flash and writes data to an arbitrary destination, we know we have control over the destination flash page and address, the number of bytes to write, and the bytes to be written. But what we don't have control over is the source address, which is in RAM. That means bit 7 of H, in Z80 there's register pairs, HL is a 16-bit address, so H would be the high byte. So bit 7 of H will always be set because it has to be in RAM. And bit 1 of register IY plus 25 will remain reset. So if we could set it, as in this code, the code that wraps DE around from 8,000 back to 4,000 won't run. And then this routine will write data to an address above 8,000, which is all RAM. So it effectively would turn this command into a RAM to RAM copy instead of flash to RAM, or RAM to flash, flash to RAM. That's actually a good thing because we can use this to overwrite the data near SP, stack pointer, to all the same values, such as 8080, like in that screenshot before. So when this routine hits a return instruction, it'll jump to 8080 instead, where we can take control, clean up the stack, and return with flash still unlocked. So how do we ensure bit 1 of IY plus 25 is set, even when this routine will start out by resetting it? use something very similar to before. If we point IY minus 25 to a point in flash where bit 1 is set, then the boot code's attempt to reset it with a simple reset bit instruction, Z8 instruction, won't work because it's in ROM. So that simple, remember, modifying flash involves memory map commands to program a single byte at a time. So these set and reset instructions aren't going to do anything to data that's in ROM. So we can force it to effectively ignore the effect of executing that instruction. So that's entirely dependent on the fact that they never set IY after flash is unlocked. They set it once when the OS starts and never touch it again. So it's fixed easily enough in the OS if they would just set it again right before this code runs. But similar functionality exists in the boot code, and that can't be easily fixed. Certainly not on existing hardware, because you can't upgrade the boot code. You can only upgrade the OS. The boot code upgrades the OS. And even if they did fix it, there are a number of other flash unlock exploits that can be used. And there's about a dozen of them I've never disclosed, so if they ever decide to start getting aggressive with this, I'll fight them back. So, being able to unlock flash and modify it ourselves is nice, but if we wanted to write our own OS, we'd have to rely on custom OS receivers, which are going to be platform dependent, error prone, and just troublesome to mess with. It would be nice if we could just patch the OS and then re-sign it ourselves, or write our own OS and sign it with TI's private RSA key. But of course, they aren't going to just hand that key over to us. Flash upgradable Z80 models started out around the time that the TI-73 came out, and that was around 1997. In 1997, 512-bit RSA keys were looking pretty secure. And if you don't know, RSA strength is in the inability to factor the public key, which is an extremely large number, into 2 prime numbers. And computing power not being what it is today, that was considered impossible way back in 1997. But flash forward 10 years or so, and one person decided to give it a shot anyway on his computer. And he used something called the GNFS, the General Number Field Sieve, which at least at the time, and maybe still is, was considered the most efficient known method of factoring numbers into primes. So he kicked off the process for the 83 Plus OS signing key and let it run on his computer for about 2 months before it finally spit out the primes. So he had actually proven what was long disregarded, that it actually was possible to factor these keys after enough time passed. So he posted about it online, and very shortly after TI silenced him, they actually sent someone to his home to talk to him, strongly encouraged him not to work on this anymore or talk about it, which, as you can imagine, scared the crap out of him. But the damage was done, and the community knew it was possible. So we took the remaining 13 public keys, and we started a Boeing distributed computing project to factor the rest of them. So we had hundreds, thousands of people all helping to factor the keys as quickly as possible, and before we knew it, we had all 13 keys in just under a month, all under their nose without them finding out. Since nobody had ever had the OS keys before, or even application keys on other models, there were no tools to sign modified OSs or applications. So I made some, validated that every key was correct, and could produce OSs and flash applications that each calculator would accept, which I could do because I had all the calculators, and then published those tools along with the key files needed to use them. And that seemed to be the final straw in the security for these things. Well, it's the final straw for TI because they actually sent me a DMCA takedown notice, which, if you don't know, DMCA stands for Digital Millennium Copyright Act, which is law that basically states if you feel your copyright's being violated, you can send a takedown notice to the offender, and then that person's got 24 hours to remove the offending material. And if they don't, they have a right to sue the person. So were it not for the EFF, which is the Electronic Frontier Foundation, stepping in and offering to defend me legally against TI's threats, I would have been forced to comply with that. But the EFF sent a letter to Texas Instruments stating that you can't copyright a number, which is essentially all I published, and that they should leave me alone because it's not worth destroying a person over his calculators. TI did not respond to that letter, so the matter was dropped, and I'm still hosting all 15 FLASH12-bit keys to this day. Go download them right now. Knowing that they had lost this particular battle, TI started using Impossible to factor 2048-bit RSA keys in newly manufactured models of the TI-84 Plus and TI-84 Plus Silver Edition, which were the newest at the time. And since the hardware was never designed to validate such a large signature, validating the OS after you transfer an OS upgrade now takes 6 minutes, where before it was instantaneous. So now you have to wait around 6 minutes for it to calculate this. So that's just unacceptable. So we're going to fall back on the flash unlock exploits to undo this travesty. So to get rid of that 6-minute validation, we have to understand how the calculator boots and how OS upgrades work. When you first turn the calculator on, the boot code is the very first thing that gets controlled. So it does some basic hardware initialization, and then it checks the OS valid marker, which is stored on sector 0 with the flash chip. And if that marker is valid, it jumps into the OS and the calculator starts normal. If the marker is not valid, then it waits to receive a new valid OS over one of the link ports. And for a typical OS transfer, the first thing the boot code will do is it'll invalidate the OS both in the certificate and by erasing flash sector 0, which will reset the OS valid marker. And then in the loop, it keeps receiving small chunks of the OS over and over into RAM, and then unlocking flash, writing that to its destination, and then relocking flash back. Once that's all done, it's time for the boot code to validate the 512-bit signature in the OS, which is effectively useless now because we can generate that signature ourselves. But then it goes to validate the 24-bit signature. And if all those checks pass, it marks the OS as valid in flash sector 0 in the certificate, and then it jumps into it. So, that's pretty normal. So digging in a little further, we look at how it validates this 24-bit signature. Unlike the original 512-bit signature, this new one is stored length indexed. So that means there's a word at the beginning indicating that it's 256 bytes big, because that's how big the 24-bit signature is. And if you know the signature is 24-bit or 256 bytes, why are you storing the length? It opens up the possibility that it could be exploited, and as it turns out, yes, you can. They don't bounds check this length, so we can take advantage of that. We can embed a really, really large signature into the OS update. And because the boot code doesn't check that it's the same value, it will blindly copy the signature to the start of RAM at 8,000. So we can store 80 bytes of garbage there. And then a Z80 jump instruction, which is opcode C3, and then the address. And then we can put lots and lots and lots and lots and lots of 80s that eventually will totally overwrite RAM, including the stack. So the next time the code tries to return, it'll jump to address 8080, where we have a Z80 jump instruction. That'll jump to where we calculated our payload will actually be at. So then we get control, we get code execution. So once we get control, we can do some cleanup, such as marking the OS valid in the certificate ourselves, both there and the flash sector, because flash is unlocked, so we can modify it ourselves. And then just jump into the start of the OS. The nice thing about this is that no custom OS transfer tools are required. We just create a specially crafted OS update file with this big signature. And this exploits the read-only boot code, so all models manufactured up to that date are vulnerable, so they're screwed.
Question.
Yeah.
Why does the number 8080 keep appearing?
That's just my favorite number. It's
okay.
That same number repeated, 8080, is very near the beginning of system RAM, which is kind of a scratch space in the OS and the boot code, so it's just a convenient number to use.
That was also the model number of the one of the first 8-bit CPUs.
So it actually gets better. So another big discovery in the community, and another nail in the coffin in the security of this, has to do with modifying what should be read-only boot sectors. One thing I noticed is that the T84 Plus and 84 Plus Silver Edition boot sectors are almost identical. In fact, other than the fact that the first one has a 1 megabyte flash chip and the other one has a 2 megabyte flash chip, they are identical calculators in every way, except for one little I/O write in the boot code. So when the calculator is first booting and initializing hardware in I/O, it writes either a 0 or a 1 to I/O port 21. Now, this is a protected port, which means flash has to be unlocked before it can be written to. And by the way, you see the unlock sequence after the right before the port 21, 22, 23 writes. You don't have to have that. I don't think that even they understand how it works. You don't actually have to have that. It's only port 14 that needs that. So, they don't even know what's going on. Yeah, they actually have macros that generate all that. So, but both calculators run exactly the same OS. So the OS actually reads the value of port 21, bit 0, port 21, to determine which model it's running on. So they can have the exact same OS run on both calculators, and it's just intelligent about which one it's running on. So it's critical that it know this, because the OS is actually organized into two halves, two sections. So here's the flash layout for the T84 Plus, not the Silver Edition, this is just the regular 84 Plus, the smaller one. It has 40 hex flash pages. The first OS section is at the very beginning of the flash chip at sector 0. That's the yellow area. It runs from flash page 0 to flash page 8. And then near the end of the flash chip in green is the second part of the OS. These are the privileged pages, and that's why it has to split it up into two. The green part has got the privileged code, and then the rest has the unprivileged code. So both the upper OS range, which is in green, and the boot page in red are privileged. But the boot page is supposedly read-only. And then in between the two OS sections, that brown area is the user archive. That's where flash applications, archive variables, things like that are stored. So then here is the flash layout for the T84 Plus Silver Edition, which is twice as big. It's basically the same, except the Silver Edition's got flash chip twice as big. The boot page is now 7F instead of 3F. So it's 40 higher. And then the upper OS page range is 7C and 7D instead of 3C and 3D. This is important. The boot code initially sets the value of IO port 21, indicating which model it is, but what would happen if we unlock Flash and we modify it ourselves? So if a TD4 Plus Silver Edition writes a 0 to port 21, then the OS would believe it's actually a TD4 Plus non-Silver Edition, and vice versa. By the way, the reason I thought about doing this is I thought it would be cool to make a virus that you could run it on somebody's Silver Edition, and it would cut the Flash size in half. And no matter how much they reset the calculator, reset the OS or whatever, it wouldn't fix itself. So they have half the memory forever. So I thought that'd be cool. But that's what started all this. But yeah. And normally this would just, after writing the wrong value, normally this would just crash the calculator because suddenly it's looking at page 3C, for example, when it really wants to look at 7C and vice versa. But I had an idea that I could just, the way this virus works is I had an idea that I would just copy the upper OS pages and the boot page, so the green and red boxes, to the middle of the flash chip, ranges 3C to 3F. So that when you modify that port and the OS actually goes to look for the OS data at 3C, it would actually find it and it would continue to function normally. The thing is though, instead of the dark orange area in the middle, it would only consider that first dark orange box as the user archive. So that would effectively cut it in half. So that was the thought. It would cut that brown area in half. But when I tried to do this by changing port 21 and copying pages 7C through 7F to 3C and 3F, the copy operation wouldn't work. And it turns out there's an excellent reason for that. When I changed the value of port 21, I actually changed which range of pages was read-only. So I changed which region was read. So by changing the value of port 21, I actually changed the protection from one region to another. So all this time, we thought the flash chip was edit locked on the boot page. It was the hardware was controlling it. But no, it's just the ASIC. It's just port 21 on the ASIC that's keeping it edit locked. So by temporarily flipping the value of port 21, we can actually modify the boot code. And then there's everything I just said, making it possible to modify the boot code. And modify it, we did. We put diagnostic utilities in there. We embedded them in the boot page so that it was impossible to permanently brick it. And most importantly, we just patch out the 20 to 48-bit signature check. So naturally, when they figured out we could do this, they changed the way the calculators are manufactured. They now edit lock the boot sector on the flash chip in hardware, so the ASIC protection is actually redundant. So it's the hardware does it now. The ASIC does it and the hardware does it, but the hardware's what matters. Now here's the really fun part. Shortly after, TI came out with their first and only Z80 calculator to have a color LCD. Not only did it have a color LCD, but it had a 4 megabyte flash chip instead of a 2 megabyte flash chip, and they called it the TI4 Plus C Silver Edition, C for color. The only difference, that's the only difference between that and the older models. They even used exactly the same ASIC, even though it wasn't designed to work with a flash chip that was larger than 2 megabytes. Now the problem is the 4 megabyte flash chip has a different sector layout compared to the 1 megabyte, 2 megabyte flash chips in the older models. So the supposedly read-only pages at the end of the 2 megabyte flash chip are now in the middle of the 4 megabyte flash chip, which is now part of the new calculator's user archive, so they need to be able to modify that. But their ASIC is designed to protect against that. So what do? They use the workaround. They temporarily toggle which region is protected because they can't just turn it off. All they can do is misconfigure it in a different way, do their writes, and then toggle it back. So did they get the idea from us? I don't know who could say, but I think the timing's a little convenient on that. So the constant toggling of port 21 actually slows the calculator down to the point that performance really isn't that great. So they actually ditched that model. Don't buy it. It's really slow and awful. And they ditched it in favor of the T84 Plus CE, which is a brand new color calculator with a different EZ80 CPU. Now the EZ80 supports Z80 backwards compatibility so that you can run regular old Z80 instructions in addition to the new EZ80 ones, which support 24-bit addressing and a 16-bit I/O range instead of just an 8-bit range. Since they have 24-bit addressing now, they ditched the paging and bank switching madness in favor of a flat memory model like what you see down here. They also revamped the port protection since there are no privileged pages anymore. Now certain address ranges are considered privileged. And certain I/O ports, mainly where the high byte is 0, are considered protected and can only be written to from a privileged address range, like the red or yellow areas. The boot region at the start of the flash chips, now it's started the flash chip instead of the end. It's read-only in hardware, it's locked in hardware, and always privileged. And then the variable sized OS follows it. And then the rest of that is the user archive. Since the OS, the size of the OS can vary from version to version, the ASIC has to be configured somehow so that it knows which parts of the flash chip to consider privileged. And that privilege range is configured via protected I/O ports 001D through 001F, which can only be modified, of course, by code in the privileged region. So how do the protected I/O ports work? Well, with any privileged I/O port, right, TI must load a constant value into a register, write that value to the protected I/O port, and then immediately verify that that register contains the same constant value they just loaded. They have to do that because otherwise we could just jump right into the boot code right before the port write with our own value. So it's tedious, but they, like I said, they got a bunch of macros to do that kind of stuff. The problem though is that the OS size is variable, not constant. So it's not something that they can hard code. They can't do that with these writes specifically. So we could set our own register value and jump into the boot code right before the port 1D I/O write. And then we can still control away through a variety of means, interrupts, whatever. There's a method that's even dumber though. The EZ80, as I said, has backwards compatibility for running code in Z80 mode. The EZ80 mode has something called, something called ADL mode. That's where 24-bit addressing comes into play. But even better, any individual instruction can run in ADL mode or in Z80 mode. So in ADL mode, you can actually call a subroutine that runs in Z80 mode, and then when it returns, you're back in ADL mode. And even better than that, in the Z80 mode subroutine, you can have ADL instructions, such as those 16-bit port out and in instructions. So surely the protection on the protected I/O ports works when you're, whether you're in ADL mode or Z80 mode, right? No, no, it doesn't. So to effectively negate the protection, we just set the upper bounds of the privilege range to be really, really high, way out there, something like FE0000. So on line 27 of this screenshot, it temporarily jumps into Z80 mode to execute a single instruction, the one that writes to protected ports 1D through 1F, which really should not work, and then it returns back to ADL mode. So someone over there really should have caught this. These new models are actually way less secure than the ones from 20 years ago, and they were actually trying to improve upon it. So in my opinion, the original unlock protection used on the older models, like the 83 Plus and 84 Plus series, it's actually perfect as long as they stay on top of code-related exploits, but they didn't, and I don't think they're ever going to. But as far as this protection, the I/O port protection is likely in the ASIC just like before, and they can't fix it through software updates. And after the fact that they reused the original ASIC to make the 84 Plus C Silver Edition, and use that port 21 workaround, instead of just simply disabling that feature in the ASIC, that leads me to believe that making even minor changes to the ASIC is cost prohibitive. So this really dumb exploit is likely here to stay. They can't afford to change it to make a new ASIC to fix it. But just in case it's not, there are other ways, which I won't get into, but they exist. And just to bring things full circle, there is one new model called the T82 Advanced, which is really just a T84 Plus non-silver edition without the 2.5mm I/O port. It's European only, very locked down compared to the others. No more assembly program execution, no more flash applications transferred to the PC. They're actually hard-coded, built into the OS. And they put an LED in it, like I mentioned before, that blinks during tests instead of that I/O port. So how do we hack this thing? Well, the obvious thing is to resort back to the original T82 hacks, whose OS, even after all these years, is still pretty similar to this one. So to do that, we need RAM backups. That's normally something that happens over the 2.5mm I/O port, which we no longer have. But unbeknownst to most people, RAM backups actually do work over USB, sort of. No Link software supports it because nobody ever really bothered to look, but the code actually is there. There is code to handle it. So I came up with a memory backup, especially cracked the memory backup, with corrupted real variables, as well as a script to transfer that memory backup from a PC to the calculator using that code. And it does work. You can get code execution on it, and you can even unlock flash, same as the old ones. But then they went and released another model very similar to this one called the T84 Plus T, which is just the Silver Edition version of this one, the T82 Advanced, except they removed the backup functionality from it. So that functionality is probably going to disappear soon. So while it does work, it's probably going to go away soon. So overall, where do we go from here? Well, there's still plenty of exploits to release. Endless for the TI Inspires constantly being fought by TI, like I mentioned, so help's always appreciated there. They just went over, we need a method code, privileged code execution for the T82 Advanced, T84 Plus T. That's kind of an old school challenge. It's still outstanding. I still get emails from people really wanting code execution on this thing, especially in Europe. And it's not particularly complex. Somebody just needs to do it. I just don't have time. And then, of course, there's the T84 Plus CE family, where we need to stay on top of new developments, new hardware revisions, new OS versions. You never know when TI is going to make a manufacturing change or an OS update that has a big impact on the community. More than once, I've seen them release OS updates that have very serious bugs in them that mess up programs that have been around for decades. So, if we don't let them know about these things and the technical details that went into what went wrong and how to fix it, So, in conclusion, hopefully you've seen how these can be great educational tools. They're simple devices on the surface, but they're actually incredibly complex. They have a rich history behind them. They show up early in people's lives in high school or sometimes even earlier. For me, it was 7th grade. And the community started the community surrounding them have to deal with the same issues that you see in other communities. Things like exploit research, legal and ethical issues surrounding what you work on and release, as well as when and why. And you learn an awful lot about embedded devices, both high and low level programming, reverse engineering, game programming, I mean everything. I really cannot recommend them enough. And they get a lot of people started in programming and reverse engineering, including me, so whether you're just starting out or you just want to dig deeper into this kind of thing, I highly recommend it. Also, don't let legal threats intimidate you. If you're upsetting someone, you're probably doing something right. Standing up to that kind of intimidation's it's how change happens, so that's how you make a difference. So if you're scared...
You should know your purple text there is not readable.
Yeah, okay. They're links that I'll tell you about in a second. So, if you're scared about what you're working on, reach out. Get help. There are people out there that can help you if you need it. But first, you have to do something that requires you to get help. So don't fret. Don't put something off because of what you're afraid might happen. Do it first, and then see what you can do with it. So it's my
Just do it.
my opinion here. We've squashed a lot of problems in the calculator community over the years, but it's never over. The community needs your help, or your kids' help, or your students' help, or whatever the case may be. There's always something more to do, and even in this talk, I mentioned some of the security-related things that still need to get done. So it's important that this kind of research continue, not just in this community, but just speaking generally. So if this kind of stuff interests you, stick with it. I promise you it's worth it. So my contact information is there on the screen. This is my website, it's brandonw.net, and that is the YouTube channel. It's TA3 Programmer. It's pretty creative. You search for me to find it. So that's pretty much it. Thanks.